right? So let's talk about the fundamental objective that I want to lay the foundation for the very beginning is, let's talk about process switching versus CEF switching, right? So before I jump into what is MPLS and explain you how MPLS works, the various terms of it, the various technical pieces of MPLS architecting it, so before that, let's talk about the very fundamental piece which we all need to understand is what is process switching and what is CEF switching. Okay, so I have my notepad over here. So let's take an example of process switching versus CEF switching. Good. So process switching versus CEF switching is actually very fundamental piece of whether you are doing CCNA, CCNP, or whether you are trying to understand how networking works, right? So let's say with an example, so I've got a design over here. Okay, let's say with an example, and I want you guys to remember that particular design going forward. Okay, so I'll draw a basic diagram over here, so which I'll say that, okay, let's say I have got a couple of routers, okay, and behind the routers I'll have some sort of end users sitting in some sort of subnet, okay, and they're connected with the help of some sort of ISP between them. I'm not like drawing the ISP in the middle over here as of now, so we understand that we have some sort of ISP which has helped these two routers to get connected. And let's say this is R1, this is say branch 2, say this is R2, and let's say that this is the LAN segment behind R1, this is the LAN segment behind R2, and say this is interface Ethernet 0/0, say this is Ethernet 0/1, likewise say this is also E0/1, and say this is E0/0, and let's say the subnet, say this is 10.1.1.0/24, and say this is 10.220/24. Okay, and let's say they are connected by using some sort of network between them, which is basically a public network. Say it's 11.1.1.0/24. okay, out of which you gave some IP of say .1 to R1 and .2 to R2 from the respective subnets on the interfaces. Okay, and let's consider that this PC has got an IP address, so this is PC1. I'll consider this as the MAC address of PC1, like its name, and likewise let's say this is PC2, and this will also become the MAC address of this particular PC. And let's say this PC is having an IP address of 10.1.1.10, and this PC is having an IP address of 10.2.2.10/24. Good, and this PC is pointing to this gateway, which is say 10.1.1.1, and here I gave the IP as 11.1.1.1. Here I give the IP as 11.112. This side it is going to be 10.2.2.1, and you understand that this PC, the gateway, is basically 10.1.1.1, and here the gateway which I've configured as is 10.221. So that's my basic design over here. Good. So once you understand this, so let's talk about the fundamental piece of what is process switching versus CEF switching, right? Let's say that this PC right now wants to communicate, this PC which is 10.1.1.10 wants to communicate with 10.2.2.10, right? This guy wants to communicate with 10.2.2.10. So when the PC, which is basically the source, which is basically 10.1.1.10, wants to send some data to this destination as 10.2.2.10, Okay, so the first thing that this particular PC would do is basically it will do a binary ending to understand that the destination that I'm trying to reach, it is on the same network like my own subnet, or it is falling on a different subnet. So it knows by doing the binary ending process that it is part of 10.1.1.0/24 network. Okay, and the destination that I'm trying to reach, it is on a different subnet. So it knows that, okay, I have to send the packet to my default gateway. Okay, so it will do an ARP to find out the MAC address of the default gateway. Okay, so to find out the MAC address of the default gateway, the ARP resolution process will happen, as we all know, and it will build this particular entry in the local ARP cache. Right, it will have the entry in the local ARP cache. So now what will happen is, if you look at the local ARP cache, it will say that, okay, my gateway is 10.1.1.1. After doing the ARP resolution, then it will have the respective MAC address, which is, say, R1 E0/0 as the MAC address. So whatever MAC address is configured or it's available at E0/0 of R1, that MAC will be listed in the ARP cache of PC1. Good. So now what will happen is, you will have a layer 2. This is my layer 3 information. This will be my layer 2 information, where I'll have the source MAC. Source MAC will be PC1 MAC address, and the destination MAC would be basically the R1 E0/0 MAC address. Now this particular packet will be now generated by this particular PC, and it will be forwarded to this particular router. This router, when it receives it, it will look first of all. So I have the data, data at like payload at layer 7 somewhere here, but we are considering that whatever data I'm sending, the addressing is at layer 3 and layer 2, etc. Right. So the whole idea is, when the R1 receives this particular data, R1 will now go and look for the L2 information. It will say that, hey, the destination MAC belongs to my MAC, so it will strip off the L2 header. So it will actually strip off this entire L2 header, and then it will go and read the L3 information, and being a router, it will go and read the destination IP address. Good. And it will go and compare that with this routing table. So if you look into R1 now, R1 will have two connected routes. So it will have 10.1.1.0/24, which is connected via E0/0 as a directly connected route, and likewise it will have 11.110/24, which is directly connected via E0/1. Likewise, if you look into R2, R2 will also have two connected routes, which is 10.2.20/24 connected via E0/0 as the interface, and 11 network, which is connected via E0/1. And fortunately, we are going to run some sort of routing protocol, either it's OSPF, VRGRP, whatever, some sort of routing protocol, so that these routers can exchange those routes, and these routers can learn those routes dynamically. So let's say whatever routing protocol I'm using here as X I'm giving would be, ERGRP, RIP, whatever, right? Dynamic routing protocol, because of which, R1 will know regarding the 10.2.2.0/24, and the next hop would be 11.1.1.2. And likewise, using that same routing protocol, it will know regarding 10.1.1.0/24 network, and the next stop would be 11.1.1.1. Good. Now with that in mind, so when the packet arrived on R1 from the PC, R1 will go and look at its routing table by seeing the destination IP. The destination IP is 10.2.2.0. It says that, hey, I have got 10.2.2.0 in my routing table, and to reach it, I'm going to use this next hop, which is 11.1.1.2. Right. Now it will do what? Now it will actually, look into its local ARP cache. The router is going to look at its local ARP cache and find out that whether he knows the respective MAC address for the next hop, which is 11.1.1.2. Good. So it will look into its ARP cache. If it is there, good. If it is not there, then this R1 will start doing the ARP process from itself. So the router R1 will say that, okay, let me do an ARP and find out the MAC address of 11.1.1.2. So the ARP process will begin from R1 exit port, because to reach 11.1.1.2, this is the exit interface E0/1. The ARP request will be thrown towards this interface, and once 11.1.1.2 or this recipient forwards me the ARP response with its MAC address, I would learn that and build up my ARP cache. So now we'll say that, okay, in my ARP cache, that 11112, to reach it, it is the MAC address of E01 of R2, something like that, right? So now what will happen is, before you forward this particular packet, the router R1 will do something called as layer 2 rewrite. This is a process, right? Layer 2 rewrite, where this particular MAC address would be actually stripped off, okay, and the new MAC address entries will be written. So the new MAC address entry would be R1 E0/1 MAC, okay, which is this, and then it will be the destination MAC will be R2 E0/1 MAC address, and then the packet reaches to R2. Now again, R2, what will do, same thing. R2, when it receives the packet, it will look at layer 2. At layer 2, it will see that, hey, my MAC address, the destination MAC is matching with my interface MAC address, so I'm the recipient. Let me strip off this, layer 2 information, and we'll go and read the layer 3 information, look at the destination IP 10.2.2.10, and compare that against the routing table. It will say that, okay, it is directly connected to me, the destination, and it is via E0/0. Now before it forwards through E0/0, then it will go, before it forwards that, it will go and look into its local ARP cache and find out that if it knows the MAC address of the destination. If it does not know, then it will again do an ARP, towards the destination IP and get the resolution done and build this local ARP cache with the entry of 10.2.2.10, and this will be the MAC, say this is PC2. Once it is known, then again what will happen is this layer 2 rewrite will take place, and then the packet will be forwarded to the destination. So now the new MAC entry would be R2 E0/0, and this will be the destination MAC is for PC2, right? So this process continues, and it finally arrives at PC2. Now think about the data being as a ping request or ICMP echo request. So PC2 will naturally give an ICMP echo reply. So the echo reply process begins here. The same process also continues, right? So this is actually your process switching. That means every time the routers are getting a packet, for each and every packet, what it is doing is it is calculating. It is trying to find out that what is the corresponding layer 2 information. Right, so I send first packet. My first packet will go through the same process as I've explained you here. Similarly, when I send the second packet will also go through the same process as I have told you during the first packet journey. So because of this, the process switching is a very, very time consuming task, and it's a very processor or CPU intensive task for the devices to process these packets and analyze it and do the routing or switching functionalities. All right, so let's explain this in terms of some notes over here, so if you understand that. So let's continue with the same diagram which I've discussed. Keep this in your mind, and let's continue with the basic notes. So it says about process switching. The first thing that I wanted to tell you is the PC1 over here, whose IP address was 10.1.1.10. It wants to communicate to PC2, whose IP address is 10.2.2.10. All right. The first thing that PC1 will do is PC1 will do the binary ending process to determine that the destination is on a different network or subnet. So once the ending process is done, so next step is PC1 will go and perform an ARP resolution to figure out the MAC address of its default gateway. Good. Third step is PC1 will create the following packet structure. So your packet structure will look quite like this. So your packet will have an L2 header, an L3 header, and it will have the data at application layer, so it will have data. So let's draw the packet out for you guys. So the first thing is I'll have the data, which can be anything, followed by your layer 4 information, could be TCP or UDP, based on the type of the data, classification of the data. And once it is known, then I'll have the layer 3 information, which I will definitely go and have the first thing as PC1 MAC address, okay, followed by, let's give it a space here, this is PC1 MAC, followed by I'll have the R1 MAC, just R1 E0/0 MAC address, you understand that, and the source IP is 10.1.1.10 and the destination IP is 10.2.2.10. okay. Let's copy that. Now this is the structure, how it looks like. So what will happen is, now in the next step is the packet would go and reach R1. The packet will reach the router R1, okay. Then R1, or you can say step number 5, as R1 will strip the layer 2 header, okay. By the way, this is your data and this is basically your layer 2 header, and this is basically your layer 3 header, okay. So R1 will strip the layer 2 header, and step number 6 would be R1 will check the L3 destination IP against its routing table, okay. Once the match is found, then go and find the next hop, that is important. So for the destination IP, what is the corresponding next hop? And number 8 would be do an ARP resolution, or check the local ARP cache that corresponds the destination MAC address of the next hop IP address. Good. So once this MAC is found, then step number 9 would be R1 creates a layer 2 header, or you can say recreates a layer 2 header, and this is known as layer 2 rewrite. So this process is known as L2 rewrite, okay. Step number 10 is the new packet that goes from R1 to R2 looks like following. Okay, so I'll copy that. And this is how it looks like. So it will have the respective layer 2 header. So now basically the same thing will have, the IP address remains the same, but the point is the MAC is changing, right? So it will basically have R1 MAC, so R1 outbound MAC, you understand that, right? And R2 inbound MAC for the next hop, which I've explained you during the diagram. All right, now what R2 will do is the same L3 lookup followed by the L2 rewrite takes place on R2. Good. So same thing continues, right, as I've explained to you. So when R2 receives it, again it does the same job, And as I've told you that this happens for every packet, right? So let me write you that. So in this type of packet, every packet gets checked against the routing table. The L2 rewrite is created and the new packet is sent, right? So this is very processor intensive and time consuming task, as you all understand, right? So think about the router is receiving this packet. First packet does this job, second packet does the same job, and so on and so forth. That is the reason it's expansive in terms of CPU consumption, memory consumption, and time consumption, etc., etc. So the world has changed, and then it came up with the concept of fast switching, by the way, right? So what happens with fast switching is very simple, where it also called as route once, switch many, right? Or it was also called as route cache, in multiple terms, right? So the whole idea of fast switching was when the first packet arrived, go for packet switching for the first packet. So it's like do process switching for the first packet, okay, and do fast switching by following the cache from second packets onwards for the same destination. Okay, so the whole idea is if the packet is traveling from same source to same destination, so 10.1.1.10 wants to communicate to 10.2.2.10, the first packet will go through the concept of process switching. So now what will happen is R1 and R2 will have the ARP caches populated. So the subsequent packets, let us say the second to the 10th packet, if you're sending from the same source to the same destination, will follow the caches, and it will go and follow the process switching concept, but that is called as now as fast switching, right? So it's like you do process switching only for the first packet, but follow the cache and go for fast switching for the remaining packets. So this is kind of speeding the things up for you guys, right? So to make things much more faster, what industry developed is another concept of switching, which is basically developed by Cisco, but it is open standard now, which is called a CEF process, or it is also called a CEF switching. CEF stands for Cisco Express Forwarding, right? Now the way CEF works is very simple. CEF does not work with the routing table, right? Or you can think like CEF is proactive in nature. Okay, so the first thing what CEF does is CEF looks at the routing table. So this process is by default enabled on the routers nowadays, so you don't have to enable that. You can look into the running config and you will find that the IPCEF process is there when the iOS boots up, and you will find that all the routers are nowadays doing this concept of CEF switching. So CEF basically looks at the routing table. Okay, next thing is for every route in the routing table, or in the route table, whatever you say, it creates a L2 rewrite, a L2 rewrite header, okay, keeps it ready in a new table known as the forwarding information base, or called as FIB. Okay, so the whole idea is it is proactive in nature. So CEF basically looks at the routing table of the routers, and then it will go and create proactively a layer 2 rewrite header. So for every route that the router is having, it will go and say that, okay, what is the corresponding layer 2 or MAC of that particular IP addresses that is available in the local router, and this information is carried in a new table called as FIB, or forwarding information base. Okay, so CEF generally works with FIB, which contains the destination IP along with its MAC address. Okay, so by creating the FIB, which contains the destination network and the corresponding L2 rewrite, the router can avoid the intensive routing or route table check every time. Okay, so basically the continuous route table check is not required. So for example, now what will happen, if you remember the diagram, so in my FIB table, if I look, which is auto populated by CEF, it will have that, okay, to reach 10.2.20/24 network, you have to use the source MAC will be the MAC of R1, and the destination MAC will be the MAC of R2. So this is auto populated in the CEF table, or you can say in the FIB table. Okay, now so the same thing will continue. If I want to go back to the diagram over here, right, so where PC1 wants to communicate to PC2, let me copy that. So let's understand the flow over here. So if my PC1 wants to, after FIB table, if PC1, which is 10.1.1.10, wants to communicate to PC2, so the first thing is PC1 will do the binary ending process to determine that the destination is on a different network or subnet. That thing remains the same. PC1 will perform an ARP resolution to figure out the destination MAC address of its default gateway. That remains the same. PC1 will create the following structure, which is the data, PC1 MAC, the R1 MAC, that remains the same with the L3 information. Fourth step is the packet would go and reach your R1, that remains the same. R1 will strip the layer 2 header, this is also the same. Next is R1 check the L3 destination, so R1 will check the L3 destination IP against its routing table, that's wrong. So it will go and check the L3 destination against its FIB table. There is a catch, because FIB table is automatically populated by CEF, so it will go and check the FIB table instead checking the routing table. So next is go and find the next hop. Rather finding the next hop, it will go and find the destination and the corresponding L2 rewrite information. Okay, so which is available in the FIB table proactively. Step number 8 is not to do any ARP resolution here, because this is the thing that we are trying to omit with respect to process switching. Okay, so number 8 would be rewrite the layer 2 header and forward the packet. Just keep it simple, because you already have the information, right? And it will look like the following. So the whole idea is your layer 2 rewrite is not been performed by the router as a separate task. So it is a proactive task which is given to the control plane that is called as CEF. And CEF does this automatically for you, and which reduces the processor intensive task which the router was doing with process switching. So now I can see the new packet would look like the same. So the source and the destination IP remains the same, but the MAC addresses is going to be get populated from the FIB cache. All right, so I hope this is clear so far, and you understand the concept of why we need CEF switching. So the whole idea of CEF switching was to make switching of packet from one interface to another interface faster as compared to process switching or fast switching. Right, so by building this particular foundation, MPLS was laid up. Okay, MPLS was laid up, and what was developed was MPLS unicast routing. okay, as an application. And when you enable this feature of MPLS unicast routing on the local routers, which needs CEF. So if you want to enable MPLS on the local routers, ensure that CEF is enabled on those local routers. That's important, one of the prerequisites of MPLS. And once MPLS is enabled, the major goal is to make things faster or speed things faster in terms of route table lookup, in terms of the decision to take in order to forward a packet from one interface to another interface. And the way it is done, it is by using this application called as MPLS unicast routing. So the whole idea of MPLS unicast routing, as I have explained you, is to make the processing and the routing decision faster and switching the packet effectively in a much more faster manner from one network to another network, or you can say from one interface to another interface. Okay, so by giving these things as of now, I hope it is clear. I'll see you in the next part where I'll discuss regarding the concept of MPLS unicast routing and draw the fundamental pieces out of it. So thank everybody to watching, and I'll see you in the next lecture. Thank you for your time.